In the previous episode, we built the level 0 CPU, which had the ability to increment a number at a fixed memory address. Now let us take a step up in complexity and create the level 1 CPU performs arithmetic serial instructions on one 8-bit integer from any location in memory. Already sounds way more complicated, but we're missing just a few key elements to achieve this level. First of all, our current CPU can't actually compute anything besides incrementation, so let me introduce the ALU, or Arithmetic Logic Unit. This will replace our old increment unit. It's a tiny circuit inside the CPU that handles basic arithmetic operations between numbers. To understand what is an ALU more exactly, let's take a look at the SN74181, the first ALU ever, or the first single-chip ALU. You can pause here to see how it works internally, but what's really important is this table that explains exactly what the ALU does. This ALU was used for 4-bit numbers. In the logic functions column, you can clearly see the operations supported by an ALU chip. Addition, subtraction, which is just addition but we're adding the other number flipped, setting to 0, etc. This chip can compute basic math. However, we're not going to use this ALU in the series. We'll instead use the P181 by Banana Logic, which definitely exists. Yeah. It follows the same idea as the SN74181 chip, but for 8-bit numbers, and supports multiplication and division. However, before wiring it, we're going to explore a bit the ways in which computers interpret numbers. Usually, we represent 8-bit numbers by this pattern, but our new CPU should also be able to support negative numbers. Why is that necessary? The subtraction circuit requires negative values. Subtracting p is like adding the 2's complement of p. Computers see an integer in the following manner. The leftmost bit, as typically used in modern computers, represents the sign bit. It indicates if a number is positive or negative. Alright, now back to our CPU. Besides replacing the I/O with an ALU, we're also going to include a few more registers. Whoa, there are quite a few changes here, but don't get overwhelmed, since all of them are logically necessary. In fact, here is a random list of criteria our level 1 CPU needs to check. The CPU should support dynamic addresses, which means we are no longer fixed to a constant address. Think of the registers as the CPU's own memory, akin to variables in your own code. In the level 0 CPU we had an address register, which was responsible for knowing the address. We'll substitute it with an instruction register, or IR, which tells the control unit two things: what to do and how to do it. For example, an instruction register can store the following byte. The first 4 bits represent the opcode, which is the instruction itself. As you see, each value corresponds to a different operation. The second half represents either a numeric value or a memory address, depending on the instruction. Pure arithmetic operations such as add will treat the operand as an addend, while operations like jump or store, which you'll see in a moment, will treat it as a memory address. It's a compact way to store useful data in a CPU. Even though the instruction register belongs to the register space, I'll place it next to the control unit to better illustrate its wiring. What's that? The other task says the CPU should have the ability to perform multiple operations subsequently. For this, we can swap the old VR value register with an accumulator register, or ACC. The accumulator is responsible for holding a number. For example, if we want to perform 3 plus 5 all divided by 2, in assembly it might look like this. First, we are storing in the accumulator the number 3 from its memory. Then we increment the accumulator by 5. Then we shift the accumulator to the right, that simulates dividing by 2. And finally, we can store the accumulator in memory. The result is 4. And don't forget, the CPU should take into account what instruction follows next. How? We store the current instruction in a register called program counter, or PC, which the CU increments by 1 after each instruction. Of course, incrementing by 1 means moving to the next instruction in memory, because instructions are also held in memory. By the way, this is called a von Neumann architecture. As you see in this example, we assume interpret the location 2 as a memory address, which will load in the ACC. You might notice jump is the only instruction that controls where the program counter goes. We can even create loops using it. Hopefully, you understand what is the role of the new registers, which are 3: PC, IR, and ACC. Just to clarify, in real CPUs, registers are usually wider. We're using 8 bits for simplicity. We'll move to more complex CPUs that require bigger registers soon. And finally, I'm tired of this clock that requires manual touch to start the CPU. We'll replace it with an automatic clock that ticks continuously. Each tick represents a CPU activation. And hey, it's the moment to visualize how the CPU performs a more complex task. This code will divide a number by 2, then enter a loop that adds continuously 1 to the accumulator. Let's execute. The program counter is set at the start of the program. Then the instruction register is loaded. The control unit, upon reading the IR value, will ask the memory controller to load the data from memory. The accumulator is updated. Next, the program counter is incremented, the instruction register is updated, and the ALU shifts the ACC. The program counter updates again, the instruction register follows, then the ALU increments the accumulator. And from the next instruction, the program counter will return back to adding 1. That's the loop. Isn't it pretty exciting to see how a mechanism like this, which seems like magic behind the curtains, works with just a bunch of components and logical steps? Personally, at least, I'm fascinated by this, but still, we currently can't exit the loop because we don't support conditions, and we can't even add 2 numbers if they both originate in memory, or at least not in an easy way. But that's a matter for the next episode. This is our level 1 CPU, a good start, but from the next CPU we'll introduce programming features so we can actually run real code. Part 3 drops next week. See you next time.